Hey guys, so today I'm going to be talking with you about section 2.5 graphing radical functions. First, before I get started, if you did not grab the note sheet that is on the podium in the classroom, go ahead and pause the video and go grab the note sheet so that you can follow along with me. Okay, make sure you are sitting with someone to work with. You'll notice that these notes are all separated into teamwork. So what I'd like for you to do is take a moment and pause the video and attempt this teamwork part 1 with your partner, and then continue through the video throughout the notes. Okay, so taking a look at teamwork part 1, you'll notice that I've filled out the order of transformation. So you'll see in red that I have all of the horizontal changes happening in the graph. And you'll notice here it's marked that this is where you make changes to your x values. The horizontal stretch and shrink with a reflection in the y-axis, you'll notice that these are put together because these technically, the order can switch, or they can just happen together. You're then followed by your horizontal shift, which is left and right. So if we refer to this equation up here, I'm looking in this area. If I were to plug in an x value to try to find the output, I would have to multiply first, which works as my horizontal stretch and shrink. Then I would have to also reflect, which if there was a negative in here, that would be multiplied at the same time. And then I would subtract or add my horizontal shift, and then I would move on to my vertical movement. So moving on into the blue, you'll see that that is making changes to your y values. So again, vertical stretch and shrink with reflection in the x-axis is written together because this order can switch as well, or they can happen at the same time. And then finally, you have your last vertical shift up down. A side note here on the left, you'll see that I have marked that the horizontal stretch and shrink and the horizontal shift, these are always the opposite. So what do I mean by that? If I had, for example, an equation that had x plus 3, this actually means to move left 3. And then likewise, if let's say I was in a square root and I had 2x here, because something is happening to the x, I'm not actually multiplying by 2, I'm going to multiply by 1/2. And now with that information, I'd like for you to take a moment, pause the video, and attempt teamwork part 2. Keep in mind that we've done all of this graphing before, and I want you to get to a point where you choose the style of graphing that you are working with, whether that is plugging in a point or using the parent function to shift. This one challenges you to try to do this by transformation, so take a moment, see what you can come up with, and then we will discuss. So talking about teamwork part 2, the first place I'm going to start is I recognize my parent function. So you'll see that since there is a squared here, that means my parent function is actually going to be f of x equals x squared. So right here in black, I've created my parent function table, and I've graphed it here in black. So then I needed to identify my shifts. So over here, you'll see that I have all of my shifts identified. I moved right 2 because it's a liar. I reflected in the x-axis, the negative out here. I had a vertical shrink of 1/2, and then I have an up 4. So actually what can happen to graph this, you'll notice that the directions say use transformations. A transformation is applying these shifts and transformations to the parent function. So you can do that a couple ways. I could take each individual point, so for example, taking 0, 0, and then applying the movement of right 2, and then moving up 4, 1, 2, 3, 4, and you'll find that I'm on my new point here. I can also just go through and decide, okay, right movement affects the x value, so I can take my parent function of -1 and add 2, which gives me a 1 here in this table. Same for the 0, I add 2, same for the 1, I add 3. Then I have reflecting the x-axis and the vertical shrink. So again, this affected my x. These two affect my y value, as well as this one affects my y value. So I could multiply my parent functions by my -1/2. Okay, so 1 times -1/2 is -1/2, and then add my 4, which is how I would get to 3.5, and then graph it here. Again, I could also take these other points and shift them, right? I could move my movement right and left, just right, and then my up movement, and then I could do my multiplication as well. So through this process, I want you to be able to choose how you want to graph. Okay? So now please take a moment, pause the video, and attempt teamwork part 3. Notice the directions first. Graph the following parent function. So you're going to be creating a parent function by choosing your x values to plug in. The little hint down here says think about what point every parent function passes through, and then choose your other points wisely. So take a moment. So looking at the first function, this is a square root function. So what you'll notice here is that to answer the question of what every parent function passes through, that's 0, 0, because if I plug 0 in, the square root of 0 is going to give me 0. Choosing points wisely means looking at your function. If we're plugging into a square root, I want to choose values that are perfect squares. So you'll notice here that I have 0, 1, 4, and 9. I've also plugged in -1 to show you that. Can you take the square root of the negative? No, you cannot. Yes, it will give you an imaginary number. However, we are trying to graph the function accurately as a parent function. So that does not give us a real solution to graph. Okay, so then when I plug in 1, the square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. And then I graph these. Now you might be thinking, well, the square root of 4 does technically give us plus or minus 2. However, if I were to graph the negative values, that graph would end up falling down here. And then this graph itself would fail the vertical line test, which would mean it wouldn't actually be a function. So when we're graphing our square root functions, we will only be graphing our positive values. Okay, so to answer these questions about the equation itself, if you want to shift a function down, so remember our parent function was f of x equals the square root of x. Our parent function shifted down 2 is going to look like this, attaching the -2 after the square root. So you're going to treat a square root just like you do in a quadratic. Underneath the square root, attached to the x is the left-right movement, and then your plus k goes here, and our a value out front. So it works just like a quadratic, it's just a square root. Next, you have your right 5. So right 5, that's a liar, so it's next to the x. So instead of plus 5, you write -5. If you were to build off of where we left off from, you would technically have that -2 there, but I actually went back to the parent function for each one of these. And then a vertical stretch of 3 would just put a 3 out in front. Okay, moving to the cube root function. The cube root function, same idea, 0, 0 passes through because the cube root of 0 is 0. However, we have to choose wisely here because of a cube root. You want to choose values that are perfect cubes. So you'll notice my choices of -8, -1, 0, 1, and 8. And this time we can take cube root of negatives because this root number is odd. Okay, so once I plug in the cube root of -8, I get -2, and so on through the table. You'll notice the shape that this cube root is taking, so that is what a cube root function is going to look like as far as end behavior and the shape the graph takes. Looking at the equations, if I want to move left 1, that's the liar, so it becomes +1. Again, any left-right is under the root next to the x. If I want to move up 5, I just add 5 to the end. If you built off of the previous, you'd have your +1 under here. And then finally, a reflection over the x-axis is a negative out front. And again, if you continuously built from where you left off, yours might look like this. Okay, so take a minute and let's go ahead and move on to teamwork part 4. So pause the video and give this one a try. Really try to choose your choice of graphing method, whether it be plugging in or graphing by shifts. So for part 4, if you look at the first one, it says create an XY table to graph this. You'll notice that I have 2 different ways of doing this. So if you look in pink, this is just the choose wisely. So if you are someone who can just look at this equation and choose an x value that makes sense to be able to subtract 2 and then take a square root of that number, this is the plug and chug in which you're strategic and you plug in and you simplify in the equation. So for example, I chose 2 as an x value. 2 minus 2 is 0. 1/2 times 0 is 0 plus 3 gave me a y value of 3. That's one way that you can do this. Just choose values, plug them in, and simplify. Then plot them and you'll have your function. Or the other option is you can graph, and this would be by transformations. Graphing by transformations, you're not actually plugging in and solving anything. So it's going to feel like you're not taking care of the square root function, however you are. Okay, so I create my parent points. So I'm thinking about the parent function of just the square root of x. Well, parent points would be plug in 0, you get 0. Plug in 4, you get 2. Plug in 9 here, you get 3. Then you just apply the transformations. Since this is a right movement of 2, the only thing that's happening to my x values is I would be adding 2. Since this is a vertical stretch, that multiplies to the y values, and then I add the 3. So this is a y multiplier of 1/2, and then you add 3. So what I would be doing is applying the transformations from my parent points. So 0 plus 2 is 2, 4 plus 2, 6, 9 plus 2, 11. So then y, I would then be plugging in the parent y values to be able to find this final answer. So 0 times 1/2 is 0, plus 3 is 3, 2 times 1/2 is 1, 1 plus 3 is 4, 3 times 1/2 is 1.5, and 1.5 plus 3 is 4.5. You'll notice that I got the same answer either way I chose to do it. I really want you to choose what works best for you, and then you graph. If you look at the next one, you'll notice here I did my parent points. I went ahead and did it option 2. So in brown on the graph here, you'll see that the parent points are there. And what I did in purple was I looked at my shifts and I took these points and I just shifted. So I'll do this middle point to start. So to reflect the x-axis, it doesn't move because it's on 0, 0. It's 1/2 my x values. My x is 0, so it stays. And then I go up 3. So that's how I ended here. Same thing for this point here. If I reflect over the x-axis, I end up here. And then I do 1/2 times my x value. Well, my x value is 1, so that moves me here. And then I move up 3. So 1, 2, 3, and that puts me there. Okay? To describe the transformation of the progression, you just list your shifts that are happening. And now take a moment, pause the video, and try Teamwork Part 5. Here's my hint for this portion. Think about the leading coefficient, if it's positive or negative, what the basic sketch of the graph looks like, and your shifts left, right, up, and down. So for this first one, this is a square root function. So you'll notice that I have a leading coefficient's positive. The parent function takes about this shape, and it moves right 3. If you think about a domain is the x values. So you're looking at the x values. So this movement, if we moved right 3 and the parent function started here, that means it just shifted right 13. So now the domain is 13 comma infinity. Your range is how low to how high you go. So again, there's no up-down movement. So therefore this graph is going to stay at 0. So the range is 0 to infinity, 0 included. The nice thing about cubic functions, if you think about the shape, so if you look at the shape, the ends of the graph are both continuing on forever, both left, right, up, and down. So for any cubic function, no matter the shift, the domain and the range are both all real numbers, or negative infinity to infinity. And then finally, looking at our last one, we have a square root. So the leading coefficient was negative. This was reflected. So I took the parent function, which originally looks like this, and went ahead and reflected it over because that's going to affect my range. Then I noticed I have a right 2 and an up 3. So if I look at my domain, that's what's affecting my x value. So since I moved right 2, the domain is now going to go from 2 to infinity, 2 included. If my range is how low to how high, since it reflected, I start with how low. So this is negative infinity. And since I was shifted up 3, now instead of sitting here at 0, 0, because this is where it would be, it's moved up to 3. So it goes up to 3, so now it's sitting here and going down forever. So negative infinity up to 3 included is my range. Now take a moment, pause the video, and try Teamwork Part 6. So you can actually do this strictly from the graph. You'll notice here in black I graphed the parent function, and I just went from center point to this point here. It goes up 1 over 1. Look at my new function. Here's the center point. This one goes up 2 over 1. That has vertically stretched by 2. I can also notice this is my origin. Its shift was right 4 up 3. That means I go right 4 up 3. So transferring that to an equation, I would see the cube root of negative 2 x minus 4 plus 3 based on that picture. Okay, it reflects the x-axis because I noticed that my ends of my graph actually switch directions. This is also a way you can do it algebraically. The video is about to run out of time, so good luck, grab your worksheets, and I will be back on Friday to answer any questions you might have. Good luck, and I'll see you then.